So I'd like to start out by just talking about the fact that I think there's a lot of interest generally, for people to move, from component level analysis to system level analysis or system level simulation. And so, products are getting more and more complex. Products are also becoming combinations of mechanical components and then electronic type components as well. This graphic on the screen happens to be a mining vehicle. So as we look at that, so many things to consider with regards to simulation. So, but let's kind of look, very briefly a little history here. And going back to the 1980s, that's when multi-body dynamics was first started. And the focus at that point was rigid bodies. And then as we moved into the 90s, started getting into things, with the linear flexible bodies, controls, and so forth. And then as we came to 2000, got more into things like process automation, which is the idea behind the Recordine toolkits. And then a very important thing was the addition of the Recordine nonlinear flexible body capability. And then also other interfaces, things like hydraulics and so forth. And then in the past decade, then we've looked at an extension of the simulation capability by adding multi-physics simulation. And so there had already been, multi-physics capabilities in Recordine from the point of view of the multi-body dynamics, interacting with the, finite element approach for flexible bodies. So that's sort of a form of multi-physics. And then, interacting with controls, that's a form of multi-physics. And then anything else that, people were doing with function expressions and so forth. So that's what we started with. And then more recently, this extension of the multi-physics through the use of co-simulation. And specifically, we're mentioning CFD and DEM today. But the other aspect of this is with the controls interface, which includes FMI interface. There is the ability to co-simulate from that point of view in a broad way. And the controls capability does include a set of user-definable routines so that one can co-simulate with in-house software. And that's all part of the controls interface capability. So we'll talk more about this co-simulation with CFD and DEM. So that's computational fluid dynamics and discrete element modeling. And then as we look forward to what's coming in the next decade, actually the acronym MBD we thought was always multi-body dynamics. But actually now in the common media, technical media and whatnot, MBD is now model-based design. And, NAFEMS is having a conference soon talking about model-based engineering, so that'd be MBE. So the thing is, where does multi-body dynamics belong? And, what we'll be focusing on in the next decade is really trying to raise awareness of multi-body dynamics as a key enabler of MBD, meaning model-based design, and the model-based engineering for any product that might include assemblies in motion. So to be able to do all of this multi-physics simulation, then we need a platform to start with. What is the basis for the simulation? So for our activities, the platform is a multi-body dynamics platform, And what comprises that platform? Well, there's a graphical user interface. We have this process net for application development, custom application development to allow for custom process automation, and to be able to build in your own proprietary process and data, be able to access data, might be proprietary and so forth, and that's an add-on to the platform. And then the platform contains, interfaces. So we look at the flex bodies with, being able to import mode shapes, meshes, having a standard tire interface to be able to work with third-party tire models. More recently, the standard particle interface that was introduced with V9R2, which supports the CFD and the DEM. And then the controls hydraulics interface. And as we see below, all the different options there with interfacing the Simulink, AIMSIM, FMI version 2, and the common interfacing there is these plant inputs and outputs, and also being able to do internal controls modeling with the CoLink. So with all this graphical interface and the interface to these other simulation areas, all that is then stored in the model database with all these different components, which can be created through the graphical interface or through ProcessNet. We have the process automation with the toolkit, and also customization by having user subsystems that can be defined. And then, the various toolkits, as we've talked about, with track assemblies, machinery toolkits, belts, chains, gears, powertrain type of capabilities, which, we're now calling driveline. And Nelson will be talking about that in some detail later on today. But the idea is that the driveline isn't just in automotive, but it's in any application where you have some kind of power transmission. There's a potential for the use of this new driveline capability. And, things like bearings lubrication, including oil film lubrication and so forth. And then, as part of all this capability, then to have this auto design capability to do the design of experiments and optimization of the overall system, all built into the user and same user environment. And then we have, the solver capability, which really is a multi-physics solver and also a solver that's set up to accommodate the co-simulation. And then finally, we have the results processing stage of things. And then also, I'd like to make special emphasis today talking about results validation. So in looking at kind of where we're headed with regards to some of the overall brand new capabilities in this co-simulation, as we see on the right column, then we have the ParticleWorks product, which is particle-based computational fluid dynamics. And this capability is needed to correctly simulate liquids in contact with mechanical parts, and especially parts in motion. So by having this coupled system with the mechanical parts and the fluid, then we can study what kind of behavior is imparted to the fluid due to the motion of the mechanical parts. But also in the other direction, as the mechanical parts push the fluid, then the fluid pushes back, and therefore we can calculate some very insightful capabilities or data with regards to the losses in the system due to the fluids. And so that's the thing we're trying to accommodate with all these different technologies involved, is that not any one application is going to require all these different capabilities at once, or even if you tried to do it, maybe it's still too much as far as the computer requirements. But the point is, for all the many things that you do, people will need all sorts of different combinations. So we're trying to provide this very broad collection of capabilities that are accessible to you so that when you have a particular need, we're ready to accommodate it. Okay, then the middle block here on the second column, or on the right column, is talking about the discrete element modeling. So this is the ability to simulate a lot of particles that are in more of a dry state and actually are not necessarily spherical. And that's needed to represent the interaction of mechanical assemblies with bulk materials. So the applications, we'll review some here in the next few minutes, but any kind of interaction with powdery or gravelly or soils type of bulk materials can then be accommodated with this capability. And to get the correct behavior, then you need to have non-spherical particles because the actual material is not spherical, and perfectly spherical particles behave differently than the more realistic shapes would behave. So we want the realistic behavior. And then this last one, which is kind of new, especially new, brand new, is this notion of the results validation. And we've seen a lot of different validations done, but in doing that validation work, sometimes the loads that we're producing in Recordine are at locations where it's hard to measure loads in the physical testing. So we were looking for something to address this need to help people be able to obtain loads that could be directly compared with Recordine loads, but to do that in a way that was more achievable. So we'll be talking about that quite a bit in the next few minutes. All right, so to address all these different things, we have, Recordine is this multi-body dynamics platform, and we've talked in the past about particle works, I think quite a bit, and maybe a little bit less about EDM. And then the new product that we have available is called TrueLoad. And this TrueLoad was actually developed by Tim Hunter, who worked for many years for Harley-Davidson, and he had this problem of wanting to get load information at locations on the motorcycle that really couldn't be readily instrumented. So we'll talk about that quite a bit. So let's start with particle works and just kind of review. So this example here at the transmission shows oil sloshing due to the motion of the gears, and points of interest are to let me back up here. Points of interest are to be able to track the distribution of the lubricant to make sure it's reaching all the right places. And then you can look at things like pressure and coating and so forth. But the other aspect is to look at the drag on the system. And then when we look at applications like oil here in the block of an engine, then we can see again losses, and then see the distribution. And then this next one here is looking at a full vehicle going through a splash tank. We actually have a paper about this from an SAE conference, so if you would like that and haven't received it, just send us an email. We'll be glad to share that with you. So in this application, then what we're trying to study is to understand where the water goes in the chassis, and this has effects on corrosion, but also with the advent of the hybrid vehicles, the voltages in the vehicle can be much higher than they were before. Therefore, to understand where water may be going in the vehicle is very important. So this animation here is showing kind of a different splash, but it's showing as a function of velocity, the difference in behavior between all those things. So new with the V9R3 then is with this ParticleWorks interface, we have the ability to have the particles actually interact with the Recordine nonlinear flex body. So we have a vehicle dynamics model in Recordine. The tank is modeled in Recordine, and basically, as we are, let me just change this here. So with the vehicle dynamics, we get the motion of the overall vehicle, which causes sloshing of the fuel, which then impacts on the baffles. So we might be checking on the baffle to see what kind of stresses are occurring during the sloshing, which then could be the basis for calculating durability in the tank and so forth. And then, of course, the other thing of the baffles is to study, make sure that they're positioned properly to reduce the sloshing, according to the design requirements. So, go ahead. Question?
Hey, Brampton. Yeah, in that example you've got on the screen, is the flexible body in motion, or is it just got acceleration applied to the like an acceleration field applied to cause the particle motions?
Yeah. So basically, what we're doing is a true co-simulation. So the vehicle is actually going down the test track, and it's doing some steering maneuvers. So the control of the acceleration seen at the tank, that's not an input, that's actually the result of the steering motions. So the steering motion is the input. And then as the vehicle is moving side to side, then just, inertial forces are causing the particles to bump up against the baffles. And then the baffles are now Recordine nonlinear flex bodies, so they can actually deform. The deformation isn't huge in this particular case, but it could be. So actually, the next slide is going to show you a case where the flex body is very flexible. But in this case, the entire tank, as you see up here, the entire tank, including the baffles, are all part of one big Recordine flex body, F-flex body. So the true behavior, the true response will be seen because you have the flexibility modeled, and and it's really the interaction between two different things happening, but it's all being simulated together.
Okay, cool. I know you had sent me an email about it a little while ago, and I was going to talk to you when I was out there, but my plans changed, so we could follow up on it.
Yeah, right. So, I think this is a very interesting capability, because in the past we could look at sloshing behaviors, and in the case of the transmissions and the engines, to assume that the fluid was in a rigid container, is quite a good assumption because it's very stiff. But in these other applications like this fuel tank, or even, so for, consumer products like what you work with, where you have a bottle of liquid shampoo or something, if there's sloshing going on and you want to see the response of the container, which is quite flexible, that's now possible. So interesting stuff, I think. So this is showing.
And one other follow-up question on that. So as the fluid is then interacting with that and affecting the inertia in that system, as it's driving down the road. Is all of that fed back to the vehicle?
Yes, yes, it certainly is. So,
Okay.
if you were to monitor, the attachment point between the fuel tank and the chassis, I mean, there's several of them. If you were to have like the tank half full of fuel versus 1/4 full of fuel, and then looked at the reaction loads, you'd see the difference. So yeah, it's all coupled. So. Okay, great. So this next slide here, we're looking at a wash machine, a front-loading wash machine, and if you've ever seen those operate, they turn in a certain direction, come to a halt, turn in the other direction. And in this case, the Recordine F-Flex body is actually like a basic simulating a piece of clothing. You might think of it as some kind of towel or something. And you can see the interaction between the fluid, the baffle type of features on the drum of the wash machine, and then this flexible cloth. So as people are trying to optimize the design of the wash machine, it's very challenging because due to regulations, people are always pushing for reduced energy usage, but also reduced water usage. But at the same time, the manufacturer wants to have, good performance so that the consumer is happy with the result. So based upon all that, to be able to do this kind of a detailed simulation can be, I think, very interesting for the users. Okay. All right, so that was a quick review of ParticleWorks. Now let's talk a little bit about the EDIM software. So again, the EDIM software, discrete element modeling, is all about bulk materials. And for lots of equipment, they're involved with transferring or moving or driving over bulk material. And as they do so, there may be particular loadings, and the loadings are not that easy to define. In other words, if you have a excavator, some kind of digging machine is shown here on the right, upper right. What is the load on the bucket due to the bulk material? Well, that's not really an easy question to answer if you don't have this kind of capability.
Hi, Brant.
Yeah.
I have a quick question.
Yeah.
Do you know for how long the simulation ran where the vehicle was going into the water?
That one was actually created by function base, so I don't have that particular information, but I would...
Do you have any other simulations time that it took to solve?
I mean, Zach, what would your guess be on something like that? So Zach is the person who's been doing a lot of ParticleWorks runs, and so he's better able to estimate than me. But as far as this vehicle sloshing model, of course, it depends on number of particles and so forth. So we just, received this animation, but I don't know, a lot of these simulations are running, on the order of some number of hours. What do you think, Zach?
Yeah, for the one that we're looking at on the screen right now, I would give a rough guess of a minimum of a few hours, and probably a maximum. Well, I'd say probably a few hours based upon a rough guess of how many particles are there, 2 or 3 hours. But it's a little bit hard to tell how many particles are actually in the simulation. But I've run things that are somewhat similar to that in a few hours. But once it's highly dependent upon the number of particles and I guess how many elements are in your mesh as well. You can get things, if you're not careful, that will run for several days. So you do want to be a little bit careful about how many elements you have in it, but I'd say something like this could probably be done in a few hours.
Okay,
Yeah,
thank you.
And
as you
and
have
that's using GPU also, isn't it, for the particle works?
so there's two options. One is GPU, and actually you can now do multiple GPUs in co-simulation with Recordine and ParticleWorks. And then the other option is to have a, if you have a high performance computing cluster with many CPUs, that also can be very effective. So in the case where, like with some of the vehicles sloshing, through the splash tank, that one model had at least like 24 million particles. So sometimes the memory on the GPU can be a limitation when you have this huge number of particles like that. So in that case, the high performance computing cluster can be a good option. But what we're seeing is that lately, with the constant enhancements to ParticleWorks, the GPU performance is getting faster and faster. And actually, the GPU performance is really becoming just so cost effective now. It's a very compelling approach to use the GPU now. So by the way, if you're interested in more details on ParticleWorks, please just let us know. We can certainly have a webinar about ParticleWorks, and actually there's going to be a new version coming out in the first of the year 2020, and so it's going to have some interesting capabilities. So we'll probably have a separate webinar about that when we get to that point. But if you have any questions about the current version of ParticleWorks and so forth, we can always schedule a webinar for that. Okay, great questions. Thank you for those. Okay, so on the bulk materials, the EDM software has been really kind of a market leader for many years, and they actually have a lot of experience about modeling different types of soils and aggregates and so forth, and they have a lot of databases for all these different materials. And so it's a very strong tool to use with Recordine, and just like ParticleWorks with EDM, with the V9R3, you can now have these EDM particles with the DEM method can now interact also with the Recordine nonlinear flex body. So I don't have any particular examples on the particle interaction at this point, but we will in the future. So V9R3 is still kind of new. But these animations here are showing, in this case, we do have a nice interface, and this applies to both ParticleWorks and EDM, where you can actually take a belt or a chain or a track, and now with a single click, you can include all the different track links or chain links or belt segments in the model as being components that will interact with the particles. So in the case of EDM, we call these things walls. In the case of ParticleWorks, we call things vessels. But anyway, the idea here is, this is like fairly amazing to have the complexity of a tracked vehicle going over this particle-based soil. And you can see, a track in the soil being left behind, as it passes by and the compaction takes place. So this capability offers up a lot of applications in many areas, and it's not just vehicles, by the way. Some processes have non-spherical particles, different powders and different applications, anywhere from printing or consumer products or whatever, like toners and like detergent particles. All these things are non-spherical and have complex behaviors, which we can now explore, with a very broad capability of interacting with the mechanical system. So here's a four-wheel drive loader. So it's interacting with the bulk material, not only scooping it up in the bucket, but you can see how the wheels are also, going on top of the particles. And for a moment there in the animation, you can see the tire spinning as it lost traction in the particles compared to the rigid surface. So again, bidirectional capability. The bucket and the vehicle push on the particles, but the particles push back, and then you can get loads on the bucket. So the plot here is showing what those loads are during the simulation. So it's not just a matter of finding out the max load, but finding out what is the work cycle, and then based upon that, that can be the basis for doing some fatigue calculations for component life. And here we're comparing different types of materials. So it's easy to adjust various parameters in order to represent whether you have more of a gravel or more of a sticky clay and things like that. And the loads can vary quite a bit between those different types of materials. And so then you can do a design experiment and do those comparisons. Okay, now we're going to talk about TrueLoad. So this is a product from Wolfstar Technologies. And so the idea of TrueLoad is to, basically turn a component into a load transducer. And then going along in partnership with TrueLoad is a product called True QSE, which is quasi-static events. So then you can basically superimpose results, and we'll talk about how that works shortly. So these two products are bundled together. So this is kind of the base package. And then there's an optional package for doing linear dynamic events that once you have everything set up, then you can basically come up with this modal responses based upon mode shapes related to the test data, and so forth. So, one of the applications of this, first of all, we have the ability to predict loads for use with Recordine, and then also to be able to produce then accurate duty cycle information that can be used in the FEA-based fatigue software. So let's talk a little bit about how this works. So, the question is, in certain applications, what is the load? So is this animation working? Oh, miracle. Okay, I wasn't sure when I was loading it up, but anyway, in this case of off-road motorcycle, we might be interested in some of the fork loads and so forth, but we can't really instrument at the locations where we want to know what the forces are. And then if we have a Recordine model, of this motorcycle, then we want to know if our loads are correct. But the test data doesn't naturally give us the loads that we want. So we need a tool to give us loads at the right location. So basically the idea is that strain gauges can be mounted on the component where the loads are of interest, or various components. And the idea is that the strain gauges now can be freely mounted anywhere on that component where it's convenient to mount them. And then from that handful of strain gauges, then we use that information in conjunction with a finite element mesh, and we're able to then gain full knowledge of what's happening with the vehicle, including the applied loads that are actually happening with it. And and again, with some of these dynamic events, also the instrumentation that might be trying to measure the loads could get saturated, during some of these aggressive events. And so again, looking at strains that are not right at the application of the load can help get rid of some of the noise that's observed. And then once everything is correlated, then again have this way to push the data off to fatigue software for durability studies. So this is a what we call first to market solution, in that, you know, it's not like this is commonly done by many people. This is a new technique, and so that's why I thought it would be of high interest to everyone using Recordine, because of this, you know, challenge that seems to be always present of not having load information from physical tests for use for the validation of the Recordine model. So if we think about all sorts of different possible products that we might want to be evaluating, you know, these are products that TrueLoad, you know, has been applied to in various industries. So certainly with the off-road vehicles, and then, you know, the bikes and motorcycles, I think because of Tim Hunter's Harley-Davidson background, he got into that pretty quickly. But then all sorts of things, you know, the seats in race cars, landing gear type applications, and so forth. So with all these different types of models, you know, the thing that's in common is this notion of the difficulty of measuring the loads directly. And so if the loading profile is not well known, then this acronym here, GIGO, is the garbage in, garbage out. So, you know, historically this has been an issue. And when you have poor loading information, then that drives, you know, extra iterations, because you're really not understanding what's there. So, you know, using, you know, Recordine certainly is helpful to understanding loading, but to have, you know, the Recordine calculations in line with the measured loads, then is very powerful, because then you can have high assurance that you know, what you're doing is accurate, because you have these two completely different ways of determining what the loads really are, and if they're agreeing, then you really have something. But to be able to measure loads directly with load transducers, these things can be very expensive, and as you can see, kind of bulky. And, you know, in some cases, you know, some of this instrumentation is big enough that it actually throws off the loads in the component. In other words, if the instrumentation is significantly large as compared to the component, then the measuring itself is throwing off what's really happening. So they're bulky, they can be very expensive not only to purchase, but to calibrate, and also the mounting process can be very difficult. And then, you know, if the load path in the structure is changed, then your results are not accurate any longer, and so forth. So that's why the alternative to that is then to use strain gauges, you know, mounted in other locations in the component. And, you know, a lot of people have been trying to do, you know, FE approaches to understand test data, and often have had hard times validating their outputs. And because of the difficulty of measuring loads, and then also just maybe some restrictions on strain gauges, you know, they weren't able to get enough test data to really understand things. And then when the simulation, the FEA data didn't match the test data, then it was very difficult to make progress. So in some cases, then, you know, arbitrary tuning was done. So that's this bottom section talking about the so-called correlated load. You know, people would do tuning, but, you know, they really didn't have enough information to know if that tuning was appropriate or not. And so then, without having the proper load information, then if there were, you know, failures with the product, and they wanted to do some kind of design modification, then with, you know, having, you know, the poor physical test data and, you know, lack of correlation with the simulation model, then the iterations were not as productive as they could have been. So wasted time, wasted dollars. So a lot of things people are doing right. High fidelity models, skilled finite element analysts, great software, great testing, instrumentation, equipment, data processing, great fatigue software. But on the other hand, people are finding too many variables to manage. Where do you put the gauges? If you are going to use a strain gauge approach, what are the different load cases? There's lots of data to manage and not any help in managing it. And then, unique loading situation for each data point. So this trying to work with this data is really difficult. So again, with the poor loading knowledge, then again, extra design iterations are needed, and again, the cost of dollars and time. So in this case, the idea is to measure the loads in the physical test with strain gauges, and the idea is that with the process, these complex components become basically their own load cells, and it's done by leveraging the finite element model and both the finite element model and the test data. And TrueLoad has interfaces to all the different FEA software. And part of what it's doing is letting you know what would be the optimal placement for the strain gauges. Now, if you already have test data, with strain gauges that already exist, that's okay. It will work with it and do the best that's possible. But then it can also give you feedback of how it might be better to place the strain gauges. And then the direct output to the FEA-based fatigue. So, the idea then is with the strain gauges, the process is that unit loads are applied on the finite element model, and then basically in the finite element model, you have virtual strain gauges in that you can look at the strains in different locations. And so then with that information from the unit load cases being applied to the different locations of attachment and so forth, then with all that information that's used, and then with the actual time history from the actual strain gauges, then that's applied, and then based upon that, it's using all these unit load cases to then come up with what is the true load condition that caused those strains throughout that component. So let's look at the workflow then. So starting out with all these unit load cases, and then selecting the virtual gauge placement. And so then there's this submodule called pretest that's used to evaluate where the strain gauges should go. Then you have the strain measurement of the actual physical device and the physical testing, and then you load up that strain information, and then that information is used to then create loading functions, which then are able to produce the loads in the various locations. And then with that loading, then that's can produce the duty cycles with the strain and stress histories that can be used with the fatigue software. So what is TrueLoad doing? It's first of all, this top section of the process is where the component is actually turned into a load transducer. And then with the bottom portion, as you develop the correct loading conditions, then you can use those loads to evaluate any kind of redesign and therefore do some kind of optimization.